In this tutorial, we will learn how to take the 3D architectural model and turn it into a structural analytical model, which is a model that can be used with your structural analysis software. This type of modeling greatly reduces the time of work in comparison with modeling everything again in your structural analysis software. And in this video, we will take a look at the considerations that we have to take when exporting the model. The software that we will be using for architectural modeling is ArchiCAD, while our structural analysis software is AxisVM. Now, if we look in front of us, we have a 3D model that is something that we usually receive from an architect. It consists of many structural elements, like walls, beams, slabs, etc. But it also has a lot of elements that are not necessary for structural analysis, like windows, roofs, furniture. Our task prior to exporting to structural analysis format is to determine which of these elements are structural and assign their structural parameters. For the purpose of this presentation, we will use this very simple two-story building. Its main structural elements are: so at the bottom, we have a 30 by 60 centimeter reef that goes all around the perimeter of the bottom slab. We have 20 centimeter thick concrete slabs, 30 centimeter thick masonry walls, and a roofing structure which consists of rafters and purlins. Now we will define these elements as structural. First, we will select all of the rafter beams and open the settings dialog. Under the structural analytical parameters, we will choose that the structural function is a load-bearing element, and we will tick the structural member checkbox. Here, a new drop menu opens up, and we choose standard, which means that the member will be sustainable to all of the statical internal forces. After assigning the element as structural, new allow rule-based modification options show up. We will leave all of the checkboxes on this section on, except for the offset. The offset determines the position of the member axis, and these elements must be positioned correctly. To have more control on this, we will determine the position of this offset manually. The settings in this section are rules for the element modifier. We will talk more about this a bit later, but these rules allow reshaping and optimizing the structural analysis element with the model generation rule tool. Now we will determine the axis offset for the rafters. Our model was drawn in a way that the axis of the rafter goes at the middle bottom of the beam. We correct the offset by clicking on that point in the beam picture. We could also change the offset manually by entering numbers in the EY and EZ coordinates. We select OK. Now the rafters are already assigned as structural members. Next, we will assign the purlins. We select the purlins, go to Settings dialog, and leave all of the settings the same as the rafters. The only difference is that we will have the offset as the top of the beam. So this means, because the plans that we made were made in a way that the bottom and the middle of the bottom of the rafters and the middle of the beam intersect. So this means that at this point we have a axis connection. We can even view this in a 3D structural view, and we can do that by opening View, Structural Analytical Model. Now we can already see our structural model, and these are the axes that we define. So here are the rafter axes, and these are the purlin axes. And here we can see how they intersect. Okay, now we will continue with assigning the structural elements. Next, we will assign the walls. So we select all of the walls, settings dialog, assign it as load-bearing element, and here select wall. Offset here is not that important, as it is more important that the wall has the correct height from the bottom to the top of the slab, one slab to the other. So here we can leave it like this. Okay. Next we will assign the slabs. So we select the slabs and go under the settings dialog. Next we will assign the slabs. Because the slab is made of a composite material, we must first determine which of these Let's now assign the slab. The slab is made as a composite member, so we must first assign which of the layers in this composite slab are the structural. We do that by going to Options, Element Attributes, Composites, and find the slabs that we made our slab model with. So with us, it's this one. So we have a 3-layer composite. We have 20 centimeters of reinforced concrete and 2 times 5 centimeters of different layers. So we must choose for the structural elements, we must choose here the type. We must choose the core, while the rest can be other or finish. Okay? By doing that, we have assigned only this core part of the slab to be structural. And now we just select the slabs, go to Settings dialog, and assign it its structural function as load-bearing element. We choose plate, and here we have offset, and let's choose the offset at the top of the core element, so the top of the concrete slab. So we can choose here. Okay. And the last thing that we need to assign is the bottom rib. So we choose the ribs, go to Settings dialog, and assign it as load-bearing element. The offset should be at the top, so it touches the plane of the slab. Let's now view the element in 3D. Structural analytic model. And here we can see the structural analytical model. We can also check the nodes. So here we have the element nodes. And all of the elements that are not structural are transparent. Okay. So before exporting, we can also do a model check. So under model check, physical model quality is a very simple tool that an architect can check if he has done the model correctly. So here are some rules that are very common with different element shapes, and these rules can of course be altered for your project. After clicking check, we see if there are any irregularities. So the program has returned 4 irregularities. Mostly it's wall height to length ratio, but this is not a problem. So this is because our model does not have vertical ties. There is also a more comprehensive one. There's also another option when exporting. So under the file, intercompatibility, structural analytic format SAF translators, we can choose for each type of the building material that we have assigned, we can choose the exact structural analysis format material that we wish to choose. So for concrete, for steel, aluminum, or we can add materials here. For now, we will leave this off. So this means that we will assign all of the material in our structural analysis software. So before we make the final export, I would also like to show you the structural analytical model generation rules modifier. So this is the modifier which changes the element shape so the elements fit nicely together. So this is a thing that you set in each element dialog settings. So we set it the offset manually, but if you have some smaller gaps or overhang in your model, with this tool you can modify it so everything fits nicely together. And the last thing to do now is to save the file as structural analysis format and reopen it in our structural analysis software. Okay, so now I have opened our AxisVM structural analysis software, and what we are going to do now is we are going to import the ArchiCAD file, and we are going to do some quick checks that are needed for this kind of a building. So let's just start. So I'm going to choose my code, I'm going to choose Eurocode and start a new project. And immediately I'm going to import the file that we have exported from ArchiCAD. So I go to File, Import, and open the SAF file, import file. So this is for us, AxisVM model. And here we have this model. So what we need to do first is to define the materials and some of the properties of the elements. So as you see, the model has only structural elements. It does not have any of the elements that were not marked as structural in the ArchiCAD software. Okay, so let's just go to the Elements tab and start defining the elements. So let's just first define the cross sections. So this is the rib, so it's here we have the rafter, 10 by 16, and the purlins. Okay, we are going to also add the materials that we need for modeling. So let's go under Materials tab and just add a few new materials. So we can add the characteristics here, or we can just choose the material out of the library. So we open the library and let's first insert timber material. So we are going to use timber C22 for our analysis. So we add it and confirm. We have a new material here. Let's also add concrete. So we are going to use concrete C25 through 30 for our slabs and rib. And we will also add some masonry elements for the walls. We also have a masonry library. So we have many types of masonry. I'm going to add this is a very standard brick from the manufacturer Berger. Okay. Also, what you will see here is that masonry has been defined here as isotropic. So we know that masonry does not act as 100% isotropic. So we could change some to get more exact result to orthotropic and change some of the parameters here. We can also add nonlinear properties because the masonry elements act non-linearly, but this is something that will be maybe best suited for another video. Also on the right, we have this section where we can change masonry wall design parameters. So here we can change some of the parameters and the software will automatically calculate the stiffness of the masonry wall. Okay. So let's start defining the elements. Let's first define, let's say, the slabs. So I will go here under the filter and select the slabs. Okay. Just turn to shade it. And choose the concrete material. Okay. And now these slabs have been defined, a new material. So next thing, what we will do, we will change the rib. So let's choose the rib. So it's this. So when defining the rib, it's important that here you have you have to have marked tab rib. So okay, choose the element. You can also here specify the end releases, but since this is fixed, we will not change this. This is made to be fixed. Okay, and eccentricity from the slab. Here the value is already automatically calculated correctly, so the middle of the beam to the top of the slab is 300 millimeters, as you can see here. Okay, and we have now defined the rib. Next we are going to define the roof elements, so let's first define the rafters. Let's define the rafters. This so as said before, we changed when we were doing the rib, we defined it as a rib, but here we have to define the rafter as a beam. So we will define it as a beam, change the type of material to C22. So usually this timber material is class 2, so K-def is 0.8, and this is basically it. We can confirm. Let's also change the purlins. And as you see here, all of the elements are already connected because we defined the offset in ArchiCAD. So everything is fitting together nicely. Okay, and let's also define the purlins. So the purlins. And again, we define it as beam because it's a beam element, class 2. Okay. So the last thing that we need to define now are the walls. So let's also define the walls. So walls, select all the walls. Okay. Modify. So we are going to choose masonry here, and so this is the important thing. When working with masonry, you want to change the orthography material parameters. You can do that by changing the material specifications, but I will change, because I want the forces from the wall to be transferred to the slab nicely. I will change the stiffness factor and just reduce the shear effect of the wall to 10%. So this will give us pretty good results when calculating the forces, but you can go more into details with changing the material orthography. Okay, so 10%. So why we do this? This is because we don't want to have the wall to be acting as a beam. So and it could have a positive effect on the load carrying capacity. And this, as I said, this is only done with masonry. Okay. Good, and now we have defined all of the elements. We can even take a look at the shaded view. So this is our This is our model. Okay. As you see, we only have the structural elements. Okay, when we have done this, we can now start adding loads to the model. So we go under the load section. Okay, just one more thing before we start adding loads, we must also define the support. So we are going to add a big surface support at the bottom. So let's just go to the bottom and select the bottom slab. Okay, and we can then define the stiffness of the ground. So 10,000 kilonewtons per square meter, per meter per square meter is like a standard value. So we are going to leave it like this. And now we have defined the support. Okay, so one more thing that we might also add to the elements to get a more precise calculation is to add hinges between the slab and the wall. So we would do that because we don't want the moment, so bending moments from up the wall, to be transferred to the slab, because it's masonry and concrete, so the bending moments do not transfer from wall to the slab. So we can do that by using this function edge hinge, where we select the wall and the slab and the hinge is created. But AxisVM also has a tool that very much simplifies this. So under plugins, we have this edge hinge tool. Okay, so we just define the parameters, and here, as you see, now we have hinges between the slabs and walls. Okay, so let's move on now to the loads. Let's first define the loads. We will have one permanent load case. So as you see already, it gives you all of the values of the partial values. Okay, so one permanent, one variable for live loads. So you can choose the type of building from the library, and as said, all of the factors, the partial factors, are quickly calculated automatically. Okay, and let's add another snow and a wind load. Okay. Okay, yeah, and now let's start adding loads to these load cases. So we have one ungrouped load here, so we are going to say this is a permanent load, and add another load. So let's say this first one is a permanent load of structural elements, so permanent structural, and this one should be so this is just the other elements that may be permanently on the building and have their own weight. So we will add this manually, while the permanent structure will be added automatically. So here we have another live load. Just do a live load. Here again, as I said, you can choose which type of building you have, and the values will be automatically calculated. Okay, and then snow load and wind load. Okay. Okay, so now let's start putting on the loads. So let's now start putting on the loads. First, what I will do to make my job easier, I will create two load panels. So this is a load panel. A load panel helps us to more easily define the loads on the elements. So I have created two load panels. Okay. And let's now start adding loads. So we go here, permanent structural, we just use a tool for this. So self weight, select all of the elements, okay, and now all of the elements, the structural elements, have been assigned their permanent load. We may add permanent other. So this is something that we will do manually. So we go load on the main and maybe add 1 kilonewton per square meter for extra roof weight. Okay, we may also add some extra weight to the walls. Okay, let's add another one here, and a bit more for the slabs. So because of all of the extra layers that come onto the slab, so we will add maybe -3 kilonewtons per square meter for the slab. So we choose the domain and add one here and add one here. So -3, -3. Okay. So I think we have defined the other permanent load. Now let's add the live load. So live load is usually -2. Oh, so we need to choose the point on the main. So here and here. So we have 2 times -2 on the slab, and snow load, which we will do automatically. So here we have a snow load function. We click on this, we choose that we have a pitched roof, and just select the load panels on the roof. Okay, prescribe the snow load, so I will put, for instance, 2.5. And if you have some special building shapes or extra snow accumulation, you can add it here. But since this is a very simple building, we will just leave this at off, and I can confirm. And it will now create load cases with the snow. So it has already automatically calculated, because the roof is at a 45-degree angle, it has already calculated that the snow load is not 2.5 but 1 kilonewton per square meter. And it has also automatically created load cases where you have one side of the roof more loaded than the other, and the same for the other side as well. Okay, so let's now do the wind as well. So it's a similar thing for wind as well. So we have a wind load function. We click this. For now we will just add loads on the roof. So let's add roof loads. Again, we choose the load panels. So here and here. We say it's a dual pitched roof. Based on this, the program will automatically calculate the external and internal pressure factors. So we will choose the dual pitch roof, but there are many other options as well. So we will disable the internal pressure calculation, because it will not have a big effect on the loads. And let's add, for instance, 25 meters per second of basic wind velocity. Okay, and when we click OK, the software will automatically calculate the wind load cases. So here we have cases. And now what we need to do is just do load combinations. This can be done very simply just by entering the load combinations function, and here we can define the load combination. So we just choose which type of combination we want the software to create. So we want the ultimate limit state combinations and some, let's say, just choose characteristic ones. Okay, and the software will automatically create all of the required load combinations. Okay, so we may now move to meshing. So we need to create a mesh to calculate the surface elements. So we will just click domain meshing, select all of the elements. Okay, define the size of the mesh. So 0.4 for instance is a good size mesh. Click OK, and now it has meshed the elements. We may also check the mesh. So we have 7,405 elements, and 6 of them are heavily distorted, so this is a good number. So this means that only 6 of mesh types are a bit oddly shaped, so we can even see where this is. So this is here and here, and it is mostly okay. It is mostly because we have a lot of activity here, and it made shape a bit made the mesh shape a bit differently. But this is okay. So if you have below 15 or 20 heavily distorted mesh shapes, it's okay. Okay, so now we can do the statical calculation. Okay, and now already we can see the results of the linear statical analysis. So for instance, we can just choose whichever type of result we want. So the displacement, beam internal forces, beam stresses, surface stresses, even the surface support stresses, for instance. So to see the support, and we can also change the type of result we want to represent. So this is for instance for the surface, and we can also choose the load combination. We will choose the critical maximum and minimum envelope. Okay, but so here are the results, but what we want to see is the concrete and timber design. So we will move to those tabs now. So first we will design the concrete elements. We go here, select all of the concrete elements, click OK. So here we can define some of the elements. We can choose the type of concrete, the aggregate size, the type of rebar, structural class, and exposure class. So based on this, the software calculates the concrete cover and gives you more precise results for rebar calculation. So here, if we go under the next step, we can determine the rebar parameters. So we can leave the thickness here, or we can just click here that we want it to calculate with actual thickness. And here we have we can change the bar diameters. So based on this, it will calculate the distance of the bar from the top. So we usually, for the slab, we have around, let's say, from 8 to 10 millimeters of steel in both directions. So we will just keep it at 10, so we're on the safe side. And you can of course also set the shear and the cracking parameters for the slab. Okay, and now we already have some rebar results over here. So just to see it a bit more easily, I will create stories on the model. So let's do this right now. So here is a story option. We will create a few stories, let's say a ground one at 0 meters, second one at 3 meters, and maybe a third one at 6 meters. Okay, and let's choose the ground floor. Okay. Or we can just choose the top view. And we can And now we can already see the required reinforcement values for these slabs. Here we see that we need more reinforcement. So this is right now is so in X direction bottom we need reinforcement here, so 444 square millimeters of reinforcement. In this area, let's check the Y direction. So in Y direction this direction, so we have a coordinate system here. So in this direction we also need a bit more here, and the top reinforcement, so we need most of it here because we have a very big open area here. And also one more thing, so if you remember, the thickness of the slab is 20 centimeters, which is on the low side, so the software gives us a bit higher values with the reinforcement. So in practice you would want to make this slab a bit thicker. You can change that very quickly here at this option when you are reinforcing parameters, and you can change it from 20 to, let's say, to 30, which is a bit more standard size slab, and it will reduce the required reinforcement. So okay, so this is top reinforcement for the bottom slab in X direction and top reinforcement for the Y direction. So it is all around 420, 500 here where we have a bigger opening. Okay, so the same thing for the top slab. So we can change the story. So we can be now viewing the bottom story. Let's check the top story. Okay, so this is a bit in the way, so I will hide this, and I can also hide the beams. And choose the top view. Okay, so here not a lot of top reinforcement is needed, so we only need it here where the wall is below. And let's check the X direction. So mostly here where we have a big pressure. And the bottom reinforcement in Y direction and in X direction. Okay, so these are the reinforcement results, and if you want to export your results to a report, you can easily do that just by clicking here to saving the drawing to a library and then make a report. But we have a separate video on that on our channel. Okay, so let's now lastly design the timber elements. So we can go under timber. Let's reactivate the view of the timber elements. Okay, so these are the timber elements. I'll turn this on. Okay, so now we will design the timber elements. So we will check again here the design parameters. Just choose all of the elements. Okay. So we have some of the parameters that we want in our calculation. So for ultimate limit state and serviceability limit state. So this is okay, all okay. So we will keep it as it is. And now the rafters have been designed, and we can easily view the utilization of material, for instance. So for instance, if I click on the element, here I have all of these internal statical forces. But if we wish, we can also see the utilization. So now we can very easily see the parameters here. So we can choose the analysis, so different types of analysis. So let's choose utilization. We can easily see this. So for instance, if I click on the element, so we have the utilization, and we can also have the design calculation for this member. So all of the calculations, which you can easily then export to your report. So I will show a bit more examples as well now. So this is for ultimate limit state. So you can just have different types of interactions or just internal forces. Change the type of representation. Maybe change the scale a bit, and let's change the values. Let's say so. I hope this video was helpful for you. Thank you for watching, and goodbye.